So when you start looking at stars, then you want to look at the spectrum of the star. Different stars have different spectra because they're different temperatures. Different stars have different colors because they're different temperatures. So the different spectral type stars are going to have different colors. Well, that's okay, right? I mean, you look in the sky, you see all different colors of stars. Well, maybe it's not so okay because you have some stars that are reddish and some stars that are bluish. And if you take a photograph, now this was especially true in the early days of film photography, because if you took a photograph of the star field, the stars would come out differently if they're different colors. For example, the way film was made was you had film that was made for outdoor stuff, and so blue did not show up as much. And so if you took a picture of a star field with outdoor type film, then the blue stars would look extra dim and the red stars would look extra bright. If you use film that was made for indoors, in those days, the dominant kind of light indoors was incandescent lights, which are kind of orangish. And so things look redder than they're supposed to. So if you use outdoor film indoors, everything looks red. So the indoor type film that you put in cameras was less sensitive to red light. And so if you took a picture of a star field in that sense, the red stars look extra dim and the blue stars look extra bright. And so, it became very difficult. Even your eye doesn't record brightness correctly. Different people see different colors with different intensity. It's kind of a notorious issue, for example, for men that look at star fields and they try to visually estimate the brightness of stars. They tend to get the red stars dimmer than they really are. And so so that means it becomes difficult to really tell. Even CCDs or photometers are sensitive to different colors of light slightly differently. So that means that truly comparing the brightness of a red star to one that's something else is going to be difficult. So that's when astronomers come along and they use filters. So we have U, B, V, and actually there's also an R and an I, okay, filter that you put on the camera. So the U filter primarily lets ultraviolet light through. The B filter lets the blue and purple and violet in the spectrum through. The V filter lets the middle of the spectrum through. The R filter lets the red into the spectrum through. And the I filter is primarily infrared light. So what you would do is you'd use a B filter and measure two stars, and then you find, well, what's the B magnitude? Okay, and then you can use the R filter and find what's the red magnitude, or the V filter and find the visual magnitude. And so this way it eliminates the idea that you're sensitive to different things, because what's happening is you're only comparing one color of light to that same color of light, and so you have the same sensitivity of your instrument. Now, of course, stars that primarily give off blue light are going to look dim with the red filter, and stars that give primarily red light are going to look dim with the blue filter. Okay, so here we have a star that is a cool star. It peaks at 3,000 Kelvin. So that means it's about 1,000 nanometers is the peak. So that star is primarily giving off infrared light. It gives off more red light than it does blue light. And so to your eye, this star would look reddish because it's giving more red light than blue light. Okay. Now, what you would do is you would measure how bright it is with the B filter, measure how bright it is with the V filter, and subtract B minus V. We call that the color index. Now, to find the color index of the star, B minus V. Okay. Now, you look at the star and you say, well, which one's brighter? V. So what's B minus V? Well, the thing is, brighter means smaller number. So you have a big number minus a small number. So in this case, b minus v is greater than 0. That means it's a positive number. In this case, you have a star that's peaking in the ultraviolet, but it gives off way more blue light than red light, and so this star is going to look bluish to you when you look at it. If you use the B magnitude and the V, it's brighter in blue, but brighter means smaller number. So small number minus bigger number means that B minus V is less than 0. So this star will have a color index that is negative. Star like this, about 5,500 Kelvin, something like that. It peaks near the middle of the visual spectrum. You have like all the different colors in there, so that's going to look kind of whitish to you. And so the B and the V are going to be almost identical, so B minus V is going to be close to 0. Okay. So what you could do is you could measure the B and the V. Now, this actually turns out to be a lot easier way of finding temperature than spectral lines, because with modern astronomy we have CCD cameras. So what you do is you put a B filter on the CCD camera, you take a picture of a star field, then you take a V filter and you put it on the CCD camera and you take a picture with the V filter. Then you just tell the computer subtract those two pictures, and then you get plus and minus numbers for all the stars in the picture. Well, now you know the temperature and therefore the spectral type. Whereas the other way of doing this would mean that you would have to actually look at the spectrum of each one of those stars and analyze the spectral lines in order to figure out the spectral type. So the B minus V, or the color index, quickly, once the technology came along to just have computers do the whole thing, the best and simplest and easiest way of finding the spectral characteristics of a star. Okay. Now, if you want to know the exact chemical composition, you got to actually look at the spectral characteristics, look at the spectrum again. But this would be the quickest way of just finding the temperature of a star. Okay. So color index can be B minus V, or you can even have U minus B, or V minus R, or R minus I. Any of those mean the same thing. More recently, astronomers have started using what they call color ratios, which is the blue, like the visual magnitude divided by the blue magnitude, or the blue magnitude divided by the ultraviolet magnitude. The only advantage of doing that is you always get positive numbers instead of plus and minus. I don't really like that. I prefer the B minus. And the reason I like the B minus V is with color index, you have stars, and it's a nice smooth curve here that if you find the color index, you just go up here, go over, and you get temperature. With color ratio, you can do that for part of the curve, but for part of the curve up here, it changes so fast that the tiniest little variation here corresponds to a huge change over there. And so that's why I prefer to use the color index instead of color ratio as the dominant way of what I do in terms of studying